So how many of you remember doing proof by mathematical induction? Maybe you? Or does anybody need me to go over a refresher of mathematical induction? Yes? No? You want me to? Okay. So it's a very powerful proof, and it's one that we'll be using for recursion. Mathematical induction basically, proof by induction basically says, hey, we're going to do two steps. One, prove we've got something we want to prove. We prove a base case. We prove something that is trivially easy. Okay, typically something where like basically, I know like where I should. This shows you I'm a real mathematician here, using like as opposed to such as, like n is equal to 0 or n equal to 1. Okay. Next, the next step is to assume true for some k, prove k plus 1. And the idea here is that once we assume it's true abstractly for some k, that the statement we're making is true, we assert that it's true, and then we show if it's true for k, then it's going to be true for k plus 1 as well. Now what that does for us is because we proved our base case, which is something like n is equal to 1, then proving statement 2 means that n is equal to 1. If n is equal to 1 is true, then n is equal to 2 is true. But it now acts like dominoes, where basically where it knocks each one over. 2 shows 3 is true, 3 shows 4 is true. So it allows us to, and the classical one you get in these classes like this is showing that basically the sum of numbers, of these numbers, sorry, I is equal to 1, is equal to n times n plus 1 over 2. Okay? That's kind of the classical one to show. Or as we see it posited here, 1 plus 2 plus 3 plus n minus 1 plus n is equal to n times n plus 1 over 2. That's what we typically say. All right, so step 1. Prove that it's true for n is equal to 1. Prove it's true for this. Okay, on the left that means we get 1, and on the right we get 1 times 1 plus 1 over 2, which is just a fancy way of writing 1 is equal to 1. Like I said, trivially easy to prove the base case. Step 2 shows us that says we want to prove that we assert that it's true for some k. So we say 2k, that we say that basically 1 plus 2 k minus 1. So we show that plus k. We assume that's equal to, we assume that this is true. I'm writing it really small because I'm going to reference it later. It's not a big part of it. We assume that's true. True. So now we want to prove this statement, which is 1 plus 2 plus 3 k minus 1 plus k. And I'm going to add in some parentheses, plus k plus 1. It's really hard to draw with your finger. Is equal to, and now I'm going to take my old formula and add in k plus 1 wherever I would have had an n. K plus 1 k plus 1 plus 1. I know, it's the most exciting thing on earth going on right over here. All over 2. Okay, so annoyingly though, how do we prove the thing if it's got like this dot? So I'll focus on here right now. How do we prove this thing since it has a bunch of dots in the middle? I mean, we learned a lot of rules associated to associability, commutativity, distribution, but none of them really apply when we've got dots in the middle, right? We don't know. So the key hack to this is by using what we assume is true, which is noting that this over here is just this, right? It's just this statement that this segment over here is just this segment, so we can replace it with what it's equal to. So we can rewrite it as saying k. So now what we're going to do is we're going to rewrite it. We're going to say k times k plus 1 over 2 plus k plus 1 is equal to k plus 1 times k plus 1 plus 1. I know, my handwriting, or finger writing I should say, because I'm over 2. Okay, so how in the world do we get from the left to the right? Not too bad. We are going to just simply multiply by a fancy version of 1, 2 over 2, which allows us to kind of simplify this, right? Since now they both have the denominator 2, we can just simply write it like that. And now the trickiest version of that is that we are going to extract this k plus 1 as a common factor. We're extracting this k plus 1 as a common factor, right? So that would be k plus 1 as a common factor times k plus 2, right? We had a k times k plus 1, and we had 2 times k plus 1. And then that 1 can be, this over here, we can rewrite that plus. And then let's add in some parentheses. So that's how you, so the two sides are equal. So that's proof by induction. Now this is problem 3 on your worksheet, by the way. Okay, but what if you're just like it's still 9:30 in the morning, and what if you're just looking at that and your eyes are like, it's too early for this nonsense. Okay, how in the world could I show this to you in a way that doesn't involve doing this? And what this is equivalent to, by the way, is the runtime for doing something like the unique function that you do on your ArrayList2 homework, right? Which is that we compare every item to every item to the right of it. Okay, the first item we compare to n items. The second item, or first item we compare to n minus 1 items. Second item we compare to n minus 2. Third item we compare to n minus 3, and so on and so forth. Okay. Well, let's go ahead and kind of just draw it out. The first the first item we compare to, let's say we've got 5 items. We got 5 items, so we can compare it to 5, then 4, then 3, then 2, then 1, which, I mean, that's kind of a triangular pattern, and triangles are essentially half a square, right? Except that with the way I've kind of drawn it, it's just like a bit more than half the square, and I mean, like, if you take a look, n times n plus 1, that's a bit more than half the square, n squared over, it's a bit more than n squared over 2. It's n squared plus n over 2. So graphically, this is not a proof. This is a demonstration, right? But this is why we say this is n squared rather than n, because we've got this, because if we add another row, it's going to add a bit more. The idea here is that with n squared relationships, right? Let's go back to the example of me, the teacher, because I'm making this all about me, okay? Suppose I am grading exams, right? Adding another student to, if I've got 5 exams and I add one more exam, right? I'm just adding one more unit of work. I've got another exam to grade. Great. Okay. However, let's say I'm being paranoid. Okay, let's see I'm being paranoid. And what I'm doing instead is I'm checking every answer of every student against every other answer because I'm paranoid about plagiarism for some reason. Like, so I'm checking every combination, every pair. So that's basically I'm checking 5 students plus 4 student. I'm checking 1 student against 5 other answers, and then 4, then 3, then 2, then 1, right? So if I add in another student, I suddenly have to make 6 comparisons now. 6 additional comparisons per question. Let's assume I'm just doing one question. But you get the idea. I've got to do another comparison of answers. So the difference between n squared and n, you can kind of think of it as adding another item. When you add n in O of n time, if you're adding another item, that's just one more unit of work. Adding n squared, right? If you're adding another item to n squared, you're adding essentially n more work. So it can be, but that being said, actually, so the important thing to realize, though, is that in this class, we'll see kind of this is not a great runtime. And a lot of times when you go for programming interviews, that may or may not be a good runtime. In fact, we generally consider in this class to be that, like something like this, to be basically as good as we get, n log n, which we'll see for some sorting algorithms. But in reality, if we're talking generally in the space of all of our problems, n to the dth power is a great runtime. No matter, it's like fantastic. Because there's so many problems that instead of using that runtime, end up having to use something along the lines of what we call exponential runtime, which is terrible. And that simply says we've got some base, and notice where n is, that's in the exponent. So for example, we might see something like, 2 to the n power, where, and this is terrible because every item I add, I double the amount of work I have to do. And that gets big very quickly. Now, you'll still see these algorithms sometimes used for very small runtimes, and we'll see an example of this when we go into recursion. In fact, one of the very first recursion examples that is typically taught has this runtime, even though it could be better, which is the Fibonacci sequence. All right, and for problem 4, by the way, similarly, this sequence, 1 squared plus 2 squared plus 3 squared, to the n minus 1 squared plus n squared, right? That converges to another term. If we look it up on Wikipedia, it should be n times n plus 1 times 2n plus 1, don't quote me on this, right, over 6. I forget the exact numbers, but I believe those are the exact numbers. And the important thing, though, is that there's 3 terms of n there that get multiplied together. We don't have to do the full factoring. We don't have to do FOIL and then multiply it all by n. We can just simply note that there's 3 n's that will be multiplied together. Therefore, the highest degree is going to be n times n times n, which is n cubed, right? So big O analysis can make that better. On the other hand, there are sometimes, as we'll see in future classes or in future runtimes, when we get to recursive algorithms, it does get a bit trickier. And for those, we'll just simply kind of assert what the runtime is with a very broad kind of proof, but something like, we'll get something like merge sort, which has a runtime like this. 2, which is recursive, by the way. And we'll assert that, so formally merge sort, which is one of the better sorting algorithms, has this runtime, which means that we split the problem in half and solve those problems. And then it takes O of n time to put those halves back together. And this actually turns out to be simplified as O of n log n, and we learn more about that later on. So there are more complicated runtimes, but a lot of times these complicated runtimes can be reduced into a much simpler kind of statement by using some very cool properties. But again, that's discussion for later, and this is more of a programming course, not a math course. Okay, so let's see. All right.